Thank you. Hi, everyone. Thank you, Nicolas, for the presentation and introduction, and thank you for inviting me, Nicolas and Steve. It's a great honor to be here. And I told Steve a few days ago, I think it was on the gala, that I always like to be the last one presenting, or one of the last ones, because then you get the feel of the audience and you understand how to tweak the presentation in order to please the audience. And it's really very interesting and exciting to be in a community with that everything talks about is digital twins, and to see that the problems that we are having, the challenges, and the solutions that we are handling it with are very the same. We have system of systems, and I'll show you something a bit similar to the same problem of vascular systems. So I'm going to talk about the Living Liver Initiative, how we progressed so far. I called it from function to flow. I would say it's basically distilling from function to flow and the future of medicine. It's a work that is being done in the Center of Excellence of Dassault System in Long Island University with a lot of my colleagues. And most of them, you'll see their names over the presentation. And if you want more information, you can come to me afterwards. And really, the essence of the collaboration is Dassault System and Baylor College of Medicine. The clinicians there are amazing. And Long Island University, which brings the engineering and researchers into the mix. So if I want you to take one thing from the presentation is that the living liver is not a dream anymore. It's becoming more and more real. The architecture of the living liver is already here. And it's going to change the way that we build medicine, the way that we address it. We saw it along all of the presentation, both of Claire this morning and of Patrick. And we know that we need to change something in how we develop medicine and how we verify medicine. And I think that the living liver is going to be a very major part in that. So I have my own Sarah, Patrick. She's 23 years old. And she was diagnosed with liver cancer a bit too late. She had all the CT scans, MRIs, and blood works on time. But even though she was diagnosed too late, and it's because all the vitals were normal for the general population, but for her, it was not. So we can only imagine what would happen if we would have a digital twin for Sarah. The most important thing in digital twins is bringing us to the vision of from figuring out, and I talk a lot with clinicians, and I really think that clinicians are like CSI detectives coming into a crime scene, trying to investigate the symptoms and see what is the underlying disease, and I really adore that. They're really trying to figure out, running some tests, trying to see what is the underlying disease, what is the progression, what is the history, with not a lot of information. And really bringing the virtual twin of the liver would be taking it from trying to figure out to really finding it out and predicting how to treat that. So why the liver? And we talked a lot about this. This is a slide that I could have skipped after 3 days of talking about virtual twins. But in essence, we know that drug development is very expensive. It takes between 12 to 16 years to develop a drug, $1 to $2 billion in investment. And recently, 2 years ago, I think, there was a paper published by Sam et al. Claiming that 90% of it failed. So we're investing a lot of time, we're investing a lot of money, and at the end, we're failing. And when we look at the percentages, 40 to 50% of it is due to efficacy, and 30% due to toxicity, and the liver has a lot to do with both. So investigating the liver, understanding the efficacy and toxicity inside the liver will help us in this. In addition, you can't just talk about economics. You need to talk about the cost of life, like Sarah's life. And we know that 1 of every 3 Americans has a disease that is related to obesity called non-alcoholic fatty liver disease. And 1 to 2% of these people will need surgical or clinical intervention in order to save their liver. And I would say that somewhat of 5% of those having surgical intervention will eventually develop liver cancer. That means that we have an epidemic in front of us that we need to handle and we need to challenge. So why is it very complicated to do the liver? I've talked a lot with clinicians. They have over 500 distinct functions of the liver, from detox, protein synthesis, energy storage, regeneration. There's a lot of structures. It's a system, like a true engineer, I say, it's a system of systems. We have a lot of subsystems, the lobule, the sinusoids, the duct, the vessels, the cell, everything's inside. You have billions of macroscopic events happening in real time, and you have 6 orders of magnitude, similar to the eye. You have a lot of range, both in time, because we're talking about milliseconds of blood flow, and we're talking about months and years of developing a disease. We're talking about nanometers up to centimeters of scale. How do you do a vascular system like that? You can do the system method. You can do other things. So it is a challenge. And I think that inside that challenge, we do want to make a living liver. So how does it look today? Today, we're taking a patient-specific liver model from MRI or CT scans that we create together. And if Claire will project her project, we'll have more of that, and we'll have not only a healthy one, but diseased one. And I'm very excited about that. We have patient-specific vascular system, and we'll talk about how we solved our way into the scales. And then we have the working unit, the lobule, which interacts the blood flow, the drug flow, with the biological reactions and damage to the liver. And of course, everything talks with the cells and with the enzymes inside of it. But when we talked with clinicians, we wanted to distill it to the essence of what we want to model. Because we can't model everything, and every time that we come and say, okay, we want to do this, we add another function, we add another system, another subsystem. So we distilled it to the 4 pillars, and it was very hard. The first one was the full organ itself, and even more than that, it was just the portal vein, just the inlet of 80% of the blood through the liver into all of the liver cells. It was the working unit, the lobule, which interacts between the blood flow, the drug flow, and the cells themselves. And we want to have information scaled down, information coming in from the organ itself into the working unit, and of course, information scaling up. We want to know how the drug goes in from the full organ to the working unit, and how, let's say, damage flows out and moves the information up from a working unit to the full organ itself. So let's go over each of the organs and see what we have. For the full organ itself, we took MRI scans, constructed a 3D model, took a PBPK model of the drug itself. This time it's Tylenol, a regular drug that we have a lot of information on. We took blood pressures and velocities from one of the papers we could have taken from the living heart, and that's just an indication of what we can do later on to mix the organs together. And we created a blood flow in CFD of the velocities and concentration of the drug itself. First of all, we went to see how we're doing, because it's patient-specific, it's not synthetic, and we see that in consideration to Ma et al., it's very similar, but ours is more heterogeneous because the patient-specific is heterogeneous. And Ma et al. Is very synthetic and unified. But when we look to 4D MRIs done by Huag et al. At 2023, we see that we do have the same velocities ranges on average. We do have the same variability that they have, meaning that we are able just to plug in the blood model without changing it, put in our model of the portal vein, and getting the same range of velocities, the same span of velocities. This led us to believe that we have the working organ or the working portal vein that we consider an organ for blood and drug flow. The second one was the virtual working unit, which is a digital lobule. In essence, what it does, it has 6 inlets bringing blood inside and has zonation that we implemented inside on both of all the enzymes inside the lobule itself with zone 1, 2, and 3, and different oxygen rate, GSH rate. And once we ran our model, and this model is connected to differential equations that solves the cellular interaction of APAP, once we bind them up together, we saw that we are able to predict higher drug overdoses of APAP and the damage that is created in the lobule, considering you look at these overdoses and see that you do have slightly overdoses on the upper part, and when you go and have higher overdose, you would get damage, and even damage that cannot be regenerated by the liver cells themselves. We tweaked it and tried to make it more real because hexagon is only in simulations of mechanical engineers. In real life, it looks different, and you do get different shapes, but you do get the same zonation and the same behavior. This led us to believe that at least for APAP, we have the working unit working by itself, and now the only thing that we need to do is to connect these two. So if I convinced you that both are working, now I want to convince you on how to connect them. So system of systems, the system engineering method is a good way, and it's one way. The way that we chose was surrogate models. We implemented a multiscale method of surrogate models, meaning that the resolution of MRI is down to 1.5 millimeter, if I'm not mistaken. So what we did is we ran the simulation in the portal vein itself. We took the information of the 21 outlets that we have for our patient specific and put it inside 2D simplified simulations of the smaller veins. And when we're finished with that, we took all the information and put it again in a smaller portal, in a smaller veins that led us up to the 50 microns of the vascular system of the lobule itself. It gives us two things. First, you don't run one simulation with all of the veins, which you cannot do until now. And the second thing that it gives us variability. We get from these simulations more than 100,000 different inlets of both concentration and velocities to our lobules, meaning that with one run of portal vein, we get an information that is almost similar to the amount of lobules that one person has in his own liver. So we're able to run it in parallel and still give the same variability and the same changes that a person would have to each of the lobules that we would have in our body. The interesting thing about it is when we ran it like this, and again, we calibrated nothing, we just put and plugged in everything, we were able to have, on the left you can see it, the same results of both our working unit when we had just blood pumping in the right boundary conditions, and similar to what people have in the literature. So on average, what we had is the same velocity ranges that people saw on the lobule itself, only we started from the full organ and ran it all over. I'm just showing the average itself. We do have a span, and that's the interesting part. A span of velocities, a span of concentration that later on, when we'll have heterogeneity, when we'll have disease, we'll know in which part of the organ of the liver we do have certain amounts of concentration of drug not coming, affecting, damaging. Once you have this, this is where the interesting part starts, because you have a simulation lab. We can start running things and see what happens. So on the right side, on B, what happened was that I got excited and ran, what will happen if I block the lobules, if the lobules are damaged and they can't pass any fluids inside of it. And then you see that you don't see anything coming in, and it starts to create the microhemodynamics of that, of that vascular system. As you go along and progress it, you do see that damage of the subsystem of the lobule start to change the hemodynamics and will eventually change all over the hemodynamics of the liver itself. The next thing that I want to convince you is, what about the damage upstream? What will happen if we start with the lobule and try to go up into the organ itself. So we started looking at ALD, alcohol liver disease, because it has damage that is affecting the hemodynamics. And what we said, we know that the clinicians see symptoms. They see portal hypertension, meaning higher pressure in the portal vein of the full organ of the liver. When they see it, they know that it's categorized into 4 parts, fibrosis level 1, 2, 3, and 4, and they have measurements of pressure there. And when you look at biopsy images, histopathology images, you do see the damage inside of it. So what will happen if we try to connect it with our model? Let's try to do it and see what we have. So on the left, the first thing that you see, if you start only with lobules and you put the average damage that is supposed to be, you see that it really matters if the damage is concentrated in the middle, in the central vein, or the obstruct of the lobule itself. But when you run the same, on average, damage that the lobule sees, and multiscaling it up to the portal vein, you see that you get the same ranges of pressure. So again, we're starting with damage in the lobule and running all the damage together up the stream of the information, saying that it's harder to go there. Pressure goes up in the lobule, pressure goes up in the veins, and in the total amount of the liver itself. And we see that if we take the same pressure, the same damage stages, we get the same pressure. So now that I've shown you the 4 pillars are working, the full organ, the working units, and the information running up and down, we can start researching our digital liver. So what are we doing now? Now we're working on taking specific images from paper and trying to generate, using AI, the real images of damage that is created, putting it inside our simulations and running it. So I can say that not only on average, but even for patient-specific damage, when we put the right damage in the lobule part and run it through the multiscale model, we get the same portal hypertension symptoms that clinicians see. In addition, we started moving from blood to lymph. For now, everything that I told you was just saying that the blood comes in, and then we have a factor that runs the concentration of the drug from the blood to the lymph. Let's model the lymph itself. Here, we were very amazed to see that not a lot of people work on the liver lymph, and not a lot of information is there. And this is a very interesting anecdote, because we had a lot of simulations running by Dr. Stalian, and he saw that the blood runs in certain ways. And when we talked with clinicians, and a lot of them, they didn't really know to tell us if it's working this way or are we just running nonsense in our simulations. Only recently, about a month ago, we had a presentation by a professor in Yale, and she showed us how she thinks that the lymph works. And astonishingly enough, it's exactly what we predicted in our simulations. So we just need to bind the engineers and the clinicians together to get amazing things. And the last thing, if it will work, the last thing that I want to talk about is, of course, building patient cohort, which is everybody's idea of the Holy Grail. And this led us to start to model in a more precise way everything that we're doing on the damage part, on the toxicity part, because later on we'll want to have mutations on these genes, we want to have enzyme concentration, we'll want to have patient-specific geometry, and then run everything and have it help us develop drugs. So in essence, our goals, I think, in all this are the same: to help with virtual drug development and enable virtual clinical trials. I didn't talk about non-invasive surgery planning, but we're going there at some point as well, both on the education part and planning surgeries in silico. And I would finish up with saying that we're going back to Sarah, and today, hopefully with the digital twin, the future looks much, much brighter. And we already laid the foundation of the living liver, and it's already here, and I dare you to join and say that the living heart taught us how to beat, and the living liver hopefully will teach us how to heal. Thank you.
Thank you very much.
This is yours.
Is there any question from the audience? Maybe I have one question. So in the clinical trials and in patient care, we have a lot of imaging on the liver. So do you think that we could use those information? We are not doing the imaging for this purpose, but could we envision to use those anatomical specificities of each patient to better understand how the drugs would deliver toxicities or efficacy?
Yes, I would say more than that. Having the right data that is connected, not only the MRI or CT scans, but connected to how much portal hypertension he had, what is the underlying disease, what is the history, what was the drug taken. Having this as data is something that we always look for and hope for, but using any data always helps us. All this work was done only with one MRI scan, slices of MRI scan, but one patient. So having variability of patient, like Claire announced in the morning, is something that excites me because it means that I can do a lot of different things and see how it works.
So we will definitely continue talking
Thank you.
about this project. Thank you very much.